Yes, sir.
Thank you. Hello, everyone. A very good afternoon, all of you. Welcome to the GATE Score Booster session of Signals and Systems Part 3. So till now, we have covered about the first chapter, that is Introduction to Signals and Systems. We have covered this. We have also covered the second chapter, which is LTA systems. We have covered the most important part, that is the Fourier analysis, the continuous time Fourier analysis, in which we have covered Fourier series and Fourier transform. In fact, we have also covered Laplace transform quiz questions, because every part, every chapter, we initially do quiz questions, try to understand the basics, try to understand where we do mistakes, and thereby we go to the signal booster question. So that is how our approach has been in both part 1 and part 2. And I'm sure all of you are enjoying these sessions, not only signals, whatever other subjects are happening. I'm sure all of you are enjoying it. At the same time, it's very, very important, my dear students, to ensure that you write down all the learnings that you're getting from the score booster sessions. Be it the important formulas, be it the important note points, be it the mistakes that you're performing or doing as a part of this session. Everything has to be documented, everything has to be written very clearly, so that before giving any test, whether it is a mock test series or any other test like chapter test, subject test, before any particular test, you just go through the learnings and thereby enter the exam. And all these learnings that you're going to carry with you are going to be immensely helpful for you in your GATE examination. So let us see who's part of today's session. Hello, everyone. So please comment in the chat box. Everyone, please comment in the chat box. So today we have a new participant, Moise, coming live. Hi, Siddiqui. Let's fight for the other participants as well. Rajashekar has been regular in both part 1 and part 2. Hi, Rajashekar. Good afternoon. Okay. So other students, please respond. Please keep responding. So meanwhile, let us enter into the session. Okay. So as I told, we are into the part 3. We have completed the first part and the second part. It has been quite an interactive session. I've seen students responding, interacting to each and every question, making mistakes, making correct. Okay. So all these things are very important before your GATE examination. Right. So if you remember the last session, so we have done the quiz of the Laplace transform. Now we are into the signal booster question. So there's a question number 7 in the sequence. Okay. So we have to find the Laplace transform of e power minus at ut plus e power minus bt u minus t for a less than b. For a less than b, you have to find out the Laplace transform of e power minus at ut plus e power minus bt u minus t. So let us see how many of you can find out the Laplace transform for the first part. Mr. Hangout Kare, can I know your name? Hi, Aditi. Good afternoon. So I already received an answer from Krishnan. So the answer is S by S plus A. Remember, as a part of this session, the questions are framed in such a way which make you do mistakes. Okay, so be little bit more careful, extra cautious while answering any particular question, everyone. So one more point to add here is that as a part of signals and systems, we'll be having quite a few learnings. We have to keep all the learnings along with us as we are moving ahead for the examination. It's not required that you are going to write the complete questions and solve it with each and every step. It's not required like that. Okay, so what you can do is that whenever we are discussing here, you can just focus on the problem solving part, because anyway you will be getting these notes. Okay, I will provide you these notes. It will be available in your description. Okay, so don't worry about it. Focus on the session, try to solve the problems, try to focus on solving it correct. How many papers will be given for rough use? I think there will be a booklet uh, called a scribble pad which is given. Okay, you will be having decent number of papers. I would personally suggest you to use pencil, okay, so that you can erase and you reuse it again. Even in case the extra additional is not given, not sure whether the extra additional will be given or not. Sometimes it will be given, sometimes it will not be given. So it's always recommended to use the scribble pad in a best possible manner. Yes, Priyabrata, I think we are having a discrete signal. Yes, we will be discussing about discrete Fourier transform. So let's focus on this question. I think I can see more and more participants are joining the session. So let us focus on the part A of this question. Swagatika. Hi, Swagatika. So there is an answer from Swagatika, B minus A by S plus A into S plus B. Okay. See, whenever you are solving any particular question, you have to be very clear in reading the question. The clarity is very, very important while reading the question. One of the common mistakes that is done by the students is whenever they are solving a question, for example, they look at the question, immediately they try to solve it. Step 1, step 2, step 3, without clearly reading the question. That's very good, Moise. See, for the understanding purpose, let me assign some values to A and B. Can we do that? Let me assign some values to A and B. So let me take the value of A is 1 and the value of B as 2. I hope you don't mind that 2 is obviously greater than 1, isn't it? 2 is greater than 1. So if that is the case, you're going to have e power minus t ut plus e power minus 2t u minus t, correct? So this is what we're going to have. Now recollect the concept of ROC. Recollect the concept of ROC, my dear students. Please recollect the concept of ROC, that whenever you are having e power minus t ut, can you please tell me what is the pole? What is the pole? Minus 1 is the pole here. Here minus 2 is the pole. Yes or no? Here minus 1 is the pole and here minus 2 is the pole. And it's a right-sided function. U of t is a right-sided function. It's a causal function. So we will be writing the ROC as sigma greater than right-sided ROC. So greater than, where is the pole? Minus 1 is the pole. Correct? So you're going to have sigma greater than minus 1 is going to be the ROC for the first part. Whereas coming to the second part, here it is going to be a left-sided function, isn't it? U of minus t is anti-causal function. It's a left-sided function. So thereby the ROC will be left-sided. So we'll be having a representation of sigma less than what? The pole is minus 2. So sigma less than minus 2. So let us quickly draw the ROC, how the ROC looks like. This is my sigma axis and this is my j omega axis. Yes or no, my dear students? So you're going to have an ROC which is sigma less than minus 2. Here there is a pole, minus 1 and minus 2 are the poles. So minus 1 and minus 2 are the poles. So we are going to have an ROC here. Sigma less than minus 2 is the ROC here. And here the ROC is going to be sigma greater than minus 1, isn't it? Yes or no? Sigma greater than minus 1 is the ROC. So do you have any common ROC? Every time when you are drawing an ROC, whenever you are using a linear property or you are adding the functions, the most important thing is that by the linearity property, the ROC of the resultant function will be the intersection of the resultant function will be the intersection of the two ROCs we already had, sigma greater than minus 1 and sigma less than minus 2. So whatever is the intersection part, that would be my ROC for this. Now here you can see that there is no common ROC, right? There is no intersection part whatsoever. One part is sigma greater than minus 1, the other part is sigma less than minus 2. Now, if you don't have any common ROC, is it possible to have a Laplace transform, my dear students? Is it possible to have the Laplace transform if you don't have any common ROC? If you don't have any common ROC, then implies there is no Laplace transform. Okay, so we already seen the students making mistakes, and why the mistake has happened? Because for a very simple reason, we directly write, okay, so if you're having something like e power minus a to ut, directly we'll write 1 by s plus a. Individually, there is nothing wrong with this. And if you're having a function like this, you will write minus 1 by s plus b, right? This is what we write. So this is what we think is a Laplace transform, but is it going to exist? The Laplace transform always is going to exist only when there is a common ROC. If there is no common ROC, my dear students, it is not possible for any function to have the Laplace transform. Is that clear? So the first answer, the first part, the answer is no Laplace transform. The answer is no Laplace transform. Now let us go into the second part of the question. Let us go into the second part of the question. T square minus at plus 15 u of t minus 4. So what is going to be the Laplace transform of this? What is going to be the Laplace transform of this t square minus at plus 15 u of t minus 4? What is the Laplace transform of this? What is the Laplace transform of this? So Moise is already answering the question. Very good, Moise. Other students, please try to answer it yourself. I'll give you a couple of minutes. Can I know how many students have joined late? So have you understood the first part? The other students, have you understood the first part? Yes or no? Is the first part very clear to you? Yes or no? T square minus 8t plus 15. T square minus 8t plus 15 u of t minus 4, isn't it? U of t minus 4. right? So now how to approach this question? Should we do like this? T square u of t minus 4. Find the Laplace transform of this. Minus 8 u of t minus 4. Find the Laplace transform of this. Plus 5 u of t minus 4. Find the Laplace transform of this. Are we going to do like this? Are we going to do like this? Are we going to do like this? Yes or no? We are not going to approach like this. We are not going to approach like this. Okay. So what we are going to do is that let us write it as t minus 4 whole square. I think this is 15. Huh? This is not 5. This is 15, if I'm correct. So t minus 4 whole square is going to be t square minus 8t plus 16, isn't it? T square minus 8t plus 16 is what we are going to have. So here you are having 15. So let me write it as t square t minus 4 whole square minus 1. U of t minus 4. Is that clear? Can we write it like this? Can we write it like this? T minus 4 whole square minus 1. U of t minus 4. Yes or no? T minus 4 whole square minus 1 u of t minus 4. We can write like this. Yes or no? So what are we going to have? T minus 4 whole square u of t minus 4 minus u of t minus 4 minus u of t minus 4. Now let us try to use the two properties. One is multiplication by t property. If you have a u of t function having a Laplace transform as 1 by s, now u of t minus 4 will be having the Laplace transform as 1 by s into e power minus 4s, isn't it? U of t minus 4 is going to have 1 by s e power minus 4s, correct? Similarly, t into u of t is going to have a Laplace transform as what? 1 by s square. T square into u of t will be having the Laplace transform as 2 by s cube. From where are we getting this? Because we are having a property that t power n into u of t will be having the Laplace transform as n plus 1 factorial. I'm sorry, it's n factorial divided by s power n plus 1. So there is a property like this, or what you can do is that you can apply multiplication by t property. If f of t is having the Laplace transform as f of s, then t into f of t is going to have the Laplace transform as minus 1 d by ds of f of s. So you can also use this property. Every time you multiply by t, you will get the answer, right? Every time there will be a differentiation with a multiplication of minus 1. So either you can go with the formula, but this formula is not mandatory formula. I already tell you that we should only remember the mandatory formulas. Those things which can be derived, we should be comfortable deriving them. Okay, because that will ensure that our memory is there. Okay, when we are going to the examination, we know that there are only limited number of formulas which you need to remember. The other formulas can be easily derived. That will give you some confidence. Okay, rather if you are having so many formulas to remember, always you will be under tension whether you can remember it or not. Okay, so here we are trying to use the two properties. One is the time shifting property and the other is the multiplication by t property. So if this is the case, then now I can do t minus 4 whole square u of t minus 4, just the time shifting by 4 units, right? The time shifting by 4 units. Then you're going to have 2 by s cube e power minus 4s, isn't it? Yes or no? T minus 4 whole square u of t minus 4 is going to have the Laplace transform as 2 by s cube e power minus 4s. So we know the first one, u of t minus 4, its Laplace transform. T minus 4 whole square u of t minus 4, its Laplace transform. Both of them we know. Now just we have to know if this is 1, if this is 2, we just have to do 2 minus 1. That's it. If you do 2 minus 1, then you're going to have what? T minus 4 whole square u of t minus 4 minus 1. What is 1? U of t minus 4. Correct. So what is the Laplace transform going to be? What is the Laplace transform going to be? 2 by s cube e power minus 4s minus 1 by s e power minus 4s. Okay, so this is going to be the Laplace transform. This is going to be the Laplace transform. I hope all of you got the same answer. Siddiqui has got the exactly same answer. Very good. Okay, so the next part of the question. Next part of the question, everyone. Next part of the question. Next part of the question, everyone. So there is a triangular pulse, right? There is a triangular pulse. Can you please tell me what is the slope of this ramp function? What is the slope of this ramp function? What is the slope of this ramp function, everyone? What is the slope of this ramp function? In half unit, you are traveling 1 unit, right? In half unit duration, you're traveling 1 unit. It means that here we are having a slope of 2 units. Here we are having a slope of 2 units, whereas here 3 by 2 units, and here it is 1 unit. So it is 1 by 3 by 2. So can I say it is 2 by 3? Is it 2 by 3 or minus 2 by 3? Is it 2 by 3 or minus 2 by 3? You're falling, right? Whenever you're falling, it's going to be minus here. Okay, change in y by change in x. When are you going up, the slope will be positive. When are you coming down, the slope will be negative, isn't it? So now, can we represent this in the form of the ramp functions? Can we represent it in the form of ramp functions? Everyone, can we do that? Can we represent it in the form of a ramp function? What are the time instants? What are the time instants where we are having the slopes? These are the time instants where we are having the slopes, right? Here is 1, here is 2nd, here is 3rd. So can I write it as r of t? Because there is a sudden change in slope, right? So what is ramp? Ramp is nothing but sudden change in slope. So thereby here you are having a ramp. At t is equal to 0, we have a ramp, r of t. At t is equal to 1 by 2, we do have a ramp. At t is equal to 1 by 2, we do have a ramp. At t is equal to 2, we have a ramp. So there are 3 time instants where we are having the ramp. There are 3 time instants where you are having the ramp. Now, what is the coefficient of the ramp? My dear students, what is the coefficient of the ramp? What is the coefficient? The change in the value, right? The change in slope. At t is equal to 0, after this point, the slope is 2. Before this, it is going to be 0. So what is the change? The change is going to be final value minus initial value. After the change minus before the change. 2 minus 0, it is 2, isn't it? 2 minus 0, it is 2. At t is equal to 1 by 2, at t is equal to 1 by 2, after that instant, you are having minus 2 by 3. Before this instant, you are going to have 2. So we can write it as minus 2 by 3 minus 2. Minus 2 by 3 minus 2. At t is equal to 2, at t is equal to 2, after this it is 0, before this it is minus 2 by 3. So I can write it as plus 2 by 3, isn't it? I can write it as plus 2 by 3. So finally, what are we having? Finally, we have 2 into r of t minus, can you write it as 8 by 3? Is this correct? Into r of t minus 1 by 2 plus 2 by 3 r of t minus 2. So this is nothing but the representation of a signal in the form of ramp. This is nothing but the representation of the signal in the form of ramp. Now r of t, what is the Laplace transform? R of t, the Laplace transform is 1 by s square. You're going to have a 2 here, so there is a 2 here also. R of t minus 1 by 2, so it is 1 by s square, time shifting property minus 1 by 2. Yes. Okay, so it is minus s by 2. The coefficient is minus 8 by 3, so we have a coefficient of minus 8 by 3. Here, we have 2 by 3 as a coefficient, 1 by s square, which is for r of t. Now you are having r of t minus 2. So we can write it as e power minus 2s. We can write it as e power minus 2s. So this is the result of it. So 2 by s square minus 8 by 3, 1 by s square e power minus s by 2 plus 2 by 3, 1 by s square e power minus 2s. Okay. So this is the Laplace transform of the signal, the triangular pulse which is given to us. So can we move to the next question, everyone? I hope all of you have solved it. Now can we move to the next question? So this is homework, my dear students. This is a homework problem. Please take the snapshot and then we will move to the next problem. Please take the snapshot. We will move to the next problem. Everyone. Okay. Let's go to the next problem. Please take down the next problem, everyone. Please take down the next problem, everyone. So we have to find the ROC for the following signals. We have to find the ROC for the following signals, everyone. The ROC concept is very important, whether it is Laplace transform, whether it is Z transform. In both the cases, ROC is very, very important, my dear students. Okay. The first question is interesting because you are having mod of n in the power. Let's see how many of you can solve it correctly. So 1 by 3 power mod of n minus 1 by 2 power n u of n minus 1 by 2 power n u of n. Okay. So here you're having 1 by 3 power mod of n. Let us try to understand what is this mod of n. See, whenever you are having mod of n can be written as n for n greater than 0 or greater than or equal to 0, doesn't matter, and is equal to minus n for n less than 0. Okay. Now, if you're having something like a power mod of n, I can write it as a power n u of n. I can write it as a power n u of n plus a power minus n mod of n is equal to n for n greater than or equal to 0. So for n greater than or equal to 0, you are having a u of n. What is u of n in n greater than or equal to 0 region? In n greater than or equal to 0 region, u of n is nothing but 1, isn't it? So it is going to be the same thing. So for n less than 0, it is minus n. So thereby you're going to have mod of n is going to become minus n, a power minus n, u of minus n minus 1. Okay, so u of n and u of minus n minus 1 are complementary pairs. So this is applicable for, this is non-zero, it is equal to 1 for n greater than or equal to 0, and this is equal to 1 for n less than 0. So we require both of them, right? There is a region which is non-zero for n greater than 0, and there is a region which is non-zero for n less than 0. So I can represent it like this. So if that is the case, let me write this as 1 by 3 power n u of n plus 1 by 3 power minus n. 1 by 3 power minus n, can I write it as 3 power n? 1 by 3 power minus n, can I write it as 3 power n? So I can write it as 3 power n u of minus n minus 1 minus 1 by 2 power n u of n. Now here u of n is going to be the causal part, or what I can say is the right-sided part, and this part u of minus n minus 1 is going to be the anti-causal part, yes or no? This is the causal part and this is going to be the anti-causal part, or the left-sided part. So whenever you are having the sum of causal functions, or the sum of right-sided functions, the resultant ROC is going to be right-sided. Or in this case, if it's a discrete time function, we will not have a right-sided ROC. We will not have a right-sided ROC in the case of a discrete time functions. Rather, we will call it as a outside ROC, isn't it? We're going to call it as an outside ROC. So anyways, we will write it as the ROC is R greater than the outermost pole. R greater than the outermost pole. What is the outermost pole? Here 1 by 3 is the pole and here 1 by 2 is the pole. Correct? So if you are having two poles, what is the outermost pole? 1 by 2 is going to be the outermost pole, yes or no? 1 by 2 is going to be the outermost pole. So these two functions, the ROC is going to be outwards or outsided or outwards, whatever it is, and the pole it is going to be bounded is the outermost pole. So R greater than 1 by 2 is going to be the ROC here, whereas this is the left-sided function. It is very simple, R less than 3. So having R greater than 1 by 2 and R less than 3, do we have any common region? Yes, we do have the common region, that is R between that of 1 by 2 and 3. So the ROC for this function is R between the top 1 by 2 and 3. So whenever we are having the causal function, or rather I can say right-sided function, the ROC is going to be outwards in nature. The ROC is outwards in nature. If you are having a left-sided function, then the ROC is going to be inwards in nature. If you are having a group of right-sided functions, the ROC is going to be outwards, bounded by the outermost pole. Similarly, if you are having a group of left-sided functions, the ROC is going to be inwards, bounded by the innermost pole. Correct? So similarly, can we apply this concept on the next problem? You are having a right-sided function in this case. We're having a right-sided function. So can I write it as R greater than 5 by 6? Can I write it as, because very much evident that here the pole is going to be 5 by 6. So R greater than 5 by 6 is going to be the pole. The ROC. Here it is R less than 5 by 6. Now whenever you are doing the, in a way, addition, subtraction, whatever we do, both are going to satisfy the linearity property, right? Whether it is addition, whether it is subtraction, it's going to satisfy the linear property. So whenever you are adding them or subtracting them, the ROC is going to be the common region. R greater than 5 by 6. r less than 5/6. Do we have any common region? We don't have any common region whatsoever, isn't it? We don't have any common region whatsoever. So thereby the signal does not have any common ROC. The signal does not have any common ROC. So there is no Z transform for this function. So this is the case where you don't have any ROC whatsoever. We don't have any ROC whatsoever. Now let us talk about the third signal. Now let us talk about the third function. So in the third function, what are we having? Minus 1 by 9 power n u of n, minus 1 by 9 power n u of n, and then you have a minus 1 by 3 power n u of minus n. So this is what we are calling as a left-sided function, and this is nothing but a right-sided function, correct? So whenever you're having a left-sided function, right-sided function, we will individually write its ROC. What is ROC here? R greater than, is it R greater than minus 1 by 9, or is it R greater than 1 by 9? Is it R greater than minus 1 by 9, or is it going to be R greater than 1 by 9? Everyone, please try to answer this. Will it be R greater than minus 1 by 9, or it is going to be R greater than 1 by 9? Whenever you are having a power n minus a power n u of n, let us say. Now the ROC, is it R greater than minus a, or is it R greater than mod of minus a? It is always going to be mod. Okay, this is very important, my dear student. This is also a place where we do mistakes. We directly write R greater than minus a, but we know that R is radius. So a radius cannot be a negative number. Yes or no? The radius can never be a negative number. Yes or no? So thereby, we will write it as R greater than mod of minus 1 by 9. We will write it as R greater than mod of minus 1 by 9, right? Okay, so this is 3, okay? If this is not visible correctly, this is 3. So here it is R less than mod of minus 1 by 3. R less than mod of minus 1 by 3. So what is the common ROC? Do we have any common ROC? Do we have any common ROC here? It is R between the top 1 by 9 and 1 by 3, isn't it? We do have a common ROC. We do have a common ROC, that is R between the top 1 by 9 and 1 by 3. R between the top 1 by 9 and 1 by 3. So this is the correct ROC. I hope all of you got the correct answer. This is the ROC for the third signal. For the second signal, it was no ROC, and the first one it is R greater than 1 by 2. I'm sorry, R between the top 1 by 2 and 3. R between the top 1 by 2 and 3. So this concept is important. Can anyone answer the question? Whenever you are having a causal system, whenever we are having a causal system, what is the nature of ROC? Whenever we have a causal system, what is the nature of ROC? Whenever we are having a causal system, the ROC is going to be outwards in nature. The ROC is going to be outwards in nature. I'm asking about system. Similarly, if you are having a stable system, if you have a stable system, what is the condition? If you are having a stable system, what is the condition? If you are having a stable system, the ROC must include unit circle. ROC must include unit circle, isn't it? This is the condition. Yes or no? Whenever it's a stable system, the ROC has to include the unit circle. And similarly, if you want the system to be both causal and stable, if I want my system to be both causal and stable, then what is the condition? All poles must lie within the unit circle. All poles must lie within unit circle. Okay, all the poles must lie within the unit circle. All the poles must lie within the unit circle. So this is the condition. This is the condition. Is that clear, all of you? Is that clear, all of you? So let us go to the next part. Okay, so this is the homework. Please take down the homework, everyone. So we have to find x of 0. We have to find x of 0. We have to find x of 0. Please take the snap, a very quick snap. Please let me know once it is taken, everyone. Please let me know once the snap is taken. So here the Z transform is provided, ROC is already provided, and we have to find x of 0, isn't it? So now let us enter into the discrete time Fourier analysis. Discrete time Fourier analysis. My dear students, here, what are the concepts we have? DTFT, DFT, and DTFS. Now here, the most important concept is DFT. As far as DTFT is concerned, it is no different to the top what we have discussed in continuous time Fourier transform. Okay, almost the concept is going to remain the same. Okay, sometimes what we can do is that we can also derive DTFT from Z transform. We can derive DTFT from the Z transform. Okay, we will be discussing that. But our major focus needs to be on the DFT because this is more important in the examination point of view. Now, the question is that, is it there in the syllabus of electrical? The answer is yes. This year they have included the discrete time Fourier analysis. This year they have included discrete time Fourier analysis. For EC students, they have removed FFT and digital filters. These two concepts are removed, FFT and digital filters. Right? So now let us talk about the first quiz question here. The DTFT exists for U of n. Will DTFT exist for U of n? Yes or no? Will DTFT exist for U of n? First of all, let us see whether it is going to satisfy the existence condition or not. Is it going to satisfy the existence condition or not? The answer is, what is the condition? If the DTFT has to exist, the existence condition is that it has to be absolutely summable. Now this needs to be less than infinity. This is the condition. But it is infinity. But we should know one thing, that whenever we are talking about the Fourier transform, okay, so Fourier transform, even though this condition is not satisfied, even though the absolute summability condition or absolute integrability condition is not satisfied, still in few cases we find out the Fourier transform. In few cases we find out the Fourier transform. Here also what we can do is that we can write U of n in the form of the DC component and the signum function. Okay, we have the Fourier transform of a DC component and we do have a Fourier transform of the signum function. So what is the Fourier transform for the DC component? It will be pi del of n. Pi del of omega, I'm sorry. Okay, because it is 1 by 2, it is pi del of omega. If it is 1, it is 2 pi into del of omega. Now because here it is 1 by 2, it's going to be pi del of omega. What about this? You're going to have 1 by 1 minus e power minus j omega. Okay, so this is what you're going to have the Fourier transform, discrete time Fourier transform of U of n. Discrete time Fourier transform of U of n. So thereby, okay, so DTFT is going to exist. Let me give you a shortcut here. Fourier transform, whenever the Fourier transform existence condition is not satisfied, whenever the Fourier transform existence condition is not satisfied, and you see the signal is bounded, whenever the Fourier transform existence condition is not satisfied but it is bounded, then we can always find out the Fourier transform in an indirect manner. Then we can always find out the Fourier transform in the indirect manner. If this condition is satisfied, then automatically it will be having the Fourier transform. Whether it is continuous time or it is discrete time doesn't matter. Whether it is continuous time or it is discrete time doesn't matter. When the existence condition is not satisfied and the signal is bounded, we know u of n function is bounded, we can find out the Fourier transform in an indirect manner. But if the existence condition is satisfied, then we can find out the discrete time Fourier transform or continuous time Fourier transform naturally. Naturally, we can find out the Fourier transform. So the answer for this is the DTFT exists for the u of n. The DTFT exists for the u of n. Next question is that DTFT can be obtained by substituting z is equal to e power j omega. Is this correct? Is this correct that the DTFT is going to exist? The DTFT is going to exist by substituting z is equal to e power j omega. The DTFT is going to exist by substituting z is equal to e power j omega. Is this correct? Shiv Prasad is asking a question. Explain signum of n Fourier transform. See, signum of n Fourier transform, if you remember continuous time, how did we get e power minus at ut minus e power at u minus t? E power at u minus t. So both of them we know that the Fourier transform exists. Now you put limit a tends to 0. This is signum function. This is signum function. Okay, signum of t. Now what we did, we know the Fourier transform for this function, we know the Fourier transform for this function. Then you tend a to 0, then you are going to get the Fourier transform for the signum function. Similar concept we are going to do. We are going to have a function a power n u of n, and we will also have a function 1 by a power n u of minus n minus 1. Here we will be tending a to 1. Okay, so thereby we know the Fourier transform of this function, discrete time Fourier transform. We know the discrete time Fourier transform of this function. So we can tend a to 1. You will be getting the discrete time Fourier transform of the signum function. You will be getting the discrete time Fourier transform of the signum function. Okay, I hope it is clear here. Right, so the question here is that the DTFT can be obtained by substituting z is equal to e power j omega. The answer is no. Very good. I'm happy with your answer, because every time you're finding out DTFT from Z transform, every time you're finding out DTFT from Z transform, one very important thing you have to check is whether the signal satisfies the absolute summability or not. The signal satisfies the absolute summability or not. If this condition is satisfied, then yes, you can substitute z is equal to e power j omega. But if this condition is not satisfied, then you cannot do this. Then you cannot do this. Okay, so absolute summability condition needs to be satisfied. Absolute summability condition needs to be satisfied. So if this is satisfied, then no one can stop you from putting z is equal to e power j omega. You will get the DTFT directly from Z transform. But if this is not satisfied, then you cannot do this. The third question, DTFT is periodic and discrete in nature. DTFT is periodic and discrete in nature. Is this correct? The DTFT function is periodic and discrete in nature. Is this correct? The DTFT function is periodic and discrete in nature. Is this correct? Is this correct, everyone? Is this correct? DTFT is periodic and discrete. The answer is no. The answer is no. Why, sir? See, my dear students, if you are having a function f of n, this is discrete. If this is discrete, this is periodic, no doubt. But whether this is discrete or not depends upon whether this is periodic or not, whether the signal is periodic or not. Whenever we are talking about DTFT, we write it as f of e power j omega. We write it as f of e power j omega. This is DTFT. Now here, the frequency domain is continuous. The frequency domain is periodic, no doubt. The frequency domain is periodic, but it is continuous in nature. Okay, so the DTFT is periodic, but it is not discrete. It is continuous in nature. It is periodic, but it is continuous in nature. Okay, it is periodic, but it is continuous in nature. Yes or no? If you want the discrete, if you want the frequency domain to be discrete, then you will be going for DFT. If you want your frequency domain to be discrete, then you will go for DFT. So here the answer is no. The last question, the last quiz question before we go into the problem. DFT can be obtained for periodic signals. DFT can be obtained for periodic signals. DFT can be obtained for periodic signals. Is this correct? DFT can be obtained for periodic signals. Is this correct? DFT can be obtained for periodic signals. The answer is yes. DFT can definitely be applicable for periodic signals. In fact, let me go to the DTFT concept once again. If you are having a signal f of n, you are finding out DTFT. Now this DTFT is discrete and, this is continuous and periodic, right? This is continuous and periodic. Just now we have seen that. The spectrum is going to be continuous and it is going to be periodic. So on. Now, whenever you discretize it using the DFT tool, whenever you discretize it, it means that in a way you are sampling the signal. Whenever you are sampling this, then you are going to have a discrete time. Now tell me one thing, if this is discrete time, I'm sorry. Yeah. So whenever it is discrete time, automatically the other domain has to be periodic. Now, one important thing you have to understand for DFT is that DFT can be applicable for periodic signal and it can also be applicable for non-periodic signal. Okay, but if you are applying for the non-periodic signal, you are going to take a specific number of samples. Let us say n is equal to 2, n is equal to 4, n is equal to 8. So generally the radix is going to be 2. It's going to be something like 2 power r. Whatever value of n you are taking, now after that, again it is going to repeat. Even though it is non-periodic, it is going to repeat. Why, sir? Because the DFT tool forcefully makes your time domain as a periodic function. It's going to forcefully make the time domain a periodic function. Okay, so whenever out of, let us say it is non-periodic, it is having infinite number of samples. Okay, it is non-periodic and it is having infinite number of samples. Now, whenever you are having infinite number of samples, but you are only selecting finite number, like n is equal to 2, n is equal to 4, n is equal to 8, 16, 32, 64, so on. Even though, you know, non-periodic means it might be having infinite number of samples, but you are selecting only finite. And then if you apply the DFT tool, then your time domain becomes forcefully periodic. Because what happens here, it is discrete. The frequency domain is discrete. Once the frequency domain is discrete in nature, the time domain is forcefully going to become periodic in nature. The time domain is forcefully going to become periodic in nature. The answer is correct. It can definitely be applicable for periodic signals, but I'm just adding one more point here. DFT can be applicable for periodic, non-periodic, but even in the case of non-periodic, we are going to restrict the value of the number of samples. Now, once we restrict the value of number of samples and apply the DFT, now the time domain is forcefully going to become periodic in nature. The time domain is forcefully going to become periodic in nature. And this is one of the reasons why we don't generally use DTFS, discrete time Fourier series, because DFT is such a tool which can be applicable for periodic and non-periodic. Very easily we can apply for periodic and non-periodic. It's quite a famous tool. It is something that we are using in recent technologies. We are using DFT in the recent technologies. It's very famous. It can be applicable for periodic and non-periodic. Now, if it is applicable for periodic, then what is the need of DTFS? That is the reason why we generally don't use DTFS. We have a relation between DFT and DTFS coefficient. Let us say a signal is periodic. Let us say the signal is periodic and it is having a DFT as x of k. Whereas if you apply DTFS, if it is giving us CK, the same signal, it is periodic in nature, you are applying DFT, you are getting x of k, you are applying DTFS, you are getting CK. Now, there is a relation between x of k and CK. There is a relation between x of k and CK. What is that relation, sir? What is the relation we have between that of CK and x of k? Is that x of k can be given by n times that of CK. X of k can be given by n times that of CK. Okay, so this is a relation. Now, by this relation, if you know DFT, you can find out DTFS also. If you know DFT, you can find out DTFS also, where n is the period of the signal. So CK is going to be 1 by n times that of x of k. If you know CK, I can find out x of k easily. Okay, so given the choice between DFT and DTFS, we always choose DFT because this is quite a famous. This is something that we are using in a modern technology. Now, because this is famous and I can use it for periodic and non-periodic, now there is no relevance of DTFS. That is the reason why very rarely question comes from DTFS. Very rarely question comes from DTFS. See, every time if a gate thinks that a particular topic is important, every time a gate thinks that a particular topic is important, it is only important because it is somewhere related to the top of the current technology. It is somewhere related to the top of the current technology. Okay, so let us move on to the topic of DFT. Let us move on to the topic of DFT. Let us solve this problem. All of you, let us solve this problem. So this is the last problem for us. So if you are liking the session, please click on the like button. Okay. Also subscribe to the channel to get similar videos, all of you. Okay. So please note down this question and try to solve it. DFT as such, if you ask me, in the semester exam point of view, DFT is actually very calculative in nature, yes or no? I'm sure everyone who have attended, semester classes in the sense that your college classes, whoever have experienced DFT might see DFT as a very dangerous tool, right? Because it is calculatively intensive. It is calculatively intensive. Very intensive. Now, in the examination point of view, DFT revolves around very few concepts. DFT revolves around very few concepts. What is that? First of all, you should know this formula, x of k. So n is equal to 0 to n minus 1 x of n e power minus j 2 pi by n multiplied by nk. And also inverse DFT formula also you should know. Inverse DFT 1 by n summation k is equal to 0 to n minus 1 capital X of k e power minus j, in fact plus j, 2 pi by n multiplied by nk. These two you should know. And then there are some very important observations. 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 What are they, sir? First one is x of 0, the very first sample of x of k, x of 0 is going to be summation of all the samples. Is going to be summation of all the samples. Is going to be summation of all the samples. This is x of 0. Next, x of n by 2. X of n by 2 is equal to summation n is equal to 0 to n minus 1 minus 1 power n x of n minus 1 power n x of n. This is x of 0 and x of n by 2. X of 0 and x of n by 2. These two are very important in the examination point of view. Questions have come intensively in this part. There is one more observation, that capital X of k is going to be x conjugate of n minus k. X conjugate of n minus k. This is also a very important property. Okay, so using these concepts, we can easily solve many of the problems. In fact, 99% of the problems of whatever are given in the GATE examination can easily be solved. 99% of the problems can be easily solved. Remaining 1% is not in our hands. Never it will be in our hands. Okay, but many of the problems we can cover using this. Now, the first thing is that capital X of 0, as we have discussed, capital X of 0 is nothing but the summation of all the samples, isn't it? It is just the summation of all the samples. So it's going to be 5, 9, 8. Next is x of n by 2. So capital N is 4 here. So n by 2 is 2. It will be summation minus 1 power n x of n. So it is x of 0 minus x of 1 plus x of 2 minus x of 3. So it is 3 plus 1 plus 2 minus 4. So how are we doing? X of 0 minus x of 1 plus x of 2 minus x of 3, right? So it is going to be 3 plus 1 plus 2 minus 4. So what is the result? It's going to be 2, isn't it? Now let us find out x of 1. Okay. Now if x of 1 is a plus jb, let us say it is a complex number, then what will x of 3 be? If x of 1 is a plus jb, then what will x of 3 be? X conjugate of n, which is 4 minus 3. So this will be x of 1 conjugate, right? This will be x of 1 conjugate, which is a minus jb. So when I'm talking about the addition of these two samples, then it is nothing but 2a. Yes or no? It is nothing but 2a. So what I can do is that I have to just find out the real component of x of 1. I have to just find out the real component of x of 1. Let us use this formula. Where k is equal to 1 is equal to summation n is equal to 0 to 3 x of n e power minus j 2 pi by 4 multiplied by n into 1. So here this becomes 2. So summation x of n e power minus j n pi by 2, where n is 0 to 3. So I can write it as x of 0 into 1, x of 1 into e power minus j pi by 2 plus x of 2. When I put 2 here, this is going to become minus 1. When I put 2 here, then it is e power minus j pi. E power minus j pi is equal to e power j pi is equal to minus 1 plus x of 3 into e power minus j 3 pi by 2. So do we know the value of e power minus j pi by 2? E power minus j pi by 2 is going to be equal to minus j. Similarly, e power minus j 3 pi by 2 will be equal to plus j. So these are the imaginary components, and we are not interested in the imaginary components. We are just interested in the real component. So let us find out what is the real component. X of 0 minus x of 2 will be the real component. X of 0 minus x of 2 will be the real component. So can you please tell me what is x of 0 minus x of 2? Real component x of 0 minus x of 2, can you please tell me? X of 0 minus x of 2, is it 1? Is it 1? X of 0 minus x of 2 in this case will be equal to 1. I am not very concerned about what is the imaginary component. I'm not very concerned about what is the imaginary component. I just know the real component, it is sufficient. Okay, so the real component, the a, he is nothing but 1. Now it is very simple for us. X of 0 plus x of 2 divided by x of 1 plus x of 3. X of 0 plus x of 2 is nothing but what? 8 plus 2, which is 10. And x of 1 plus x of 3 will be 2. Okay, because here the real component is 1. X of 1, I'm sorry, x of 1 plus x of 3, x of 1 plus x of 3 is nothing but 2 times that of the real component. So it is simply 2, which is equal to 5. Which is equal to 5. So the answer for this question is 5. The answer for this question is 5. I can already see that the students have rightly answered this question. Students have rightly answered this question. Very good, Shiv Prasad. Very good, Rajashekar. Absolutely correct. Right. So this brings us to the end of the session. This brings us to the end of the session. So I would suggest all the students to focus on the DFT concept more. And DTFT, you just have to know the Fourier transform concept, and you have to just know the Z transform concept. Nothing special in the DFT. Even if you see the properties of DTFT, I'm sorry, I'm talking about DTFT. Even if you see the properties of DTFT, the properties of DTFT are either matching with the top of the Fourier transform, or they are matching with the top of the Z transform. Okay, so in that way, DTFT is one of the very easy topic. Once you know the continuous time Fourier transform, discrete time Fourier transform is just going to be the cakewalk. Right? So with this, we end the session from my side. So you can let me know if you are having any queries. Please let me know if you're having any queries. Okay, so Rajashekar is asking a very important question here. I'm sure many students have this concern. Whenever I find new type of problems in test series, I find it difficult to overcome. First of all, what you have to do is that you have to be confident in your previous year problems. Number one, you have to be confident in previous year problems. You should also be confident in your classroom problems. Whatever problems have been solved in the classroom, you have to be confident in it. If you want more practice, you can solve the problems from exercise book. Okay. Then if you are entering into any particular test series, okay, you are trying to solve the problem. When you're trying to solve the problem, first thing you have to do is that you should try to relate with the top of the problems that you have already solved before. You see whether this problem is related to that or not. Okay. So if it is related, then you think and try to solve the problem. Now the question comes, what if I'm not able to relate? What I would suggest in this case is that please mark the question for the review. Please mark the question for the review and go ahead, come back, and then try to solve the problem once again. Try to solve the problem once again. In majority of the cases, if you try with a fresh mind, then you will be in a position to answer it. If you are not able to answer it, then it is very simple. Once you get the solution and then you see. Now, when you are analyzing the solution, if you find the concept which is there is new, then you try to relate with the previous year questions, whether this concept is important or not. But if you realize that in the examination point of view, never the question has been asked, then don't be very serious about that particular model. Okay, so because you have gone through it, if the similar question comes in your gate examination, now you are capable enough because you have already solved a problem on this. Okay, even though you are not able to answer it in the examination, but at least you have gone through it. Maybe you will get a sense of solving it while attempting your examination. Okay, so don't be nervous. Don't think, अरे बहुत difficult question आ गया, अब कैसा करना है? Don't think like that. Try your level best, mark it for review, come back, and then try to solve it. If you are not able to solve it, check the solution after the completing the examination. If it is related to the previous year question, if the model is related to it, if the concept is related to it, then you have to take it seriously. Then you have to understand why you are not able to solve the problem in the examination. Is there any logic? If there is any logic, then you have to appreciate yourself. Shabash, आज एक और चीज सीखने के लिए मिला है. We have learned something new today. That is a learning for you. Okay, never get demotivated because of this reason. Because gate examination is very much predictive. Okay, you will be seeing majority of the questions which are based upon the previous year problems or just a modification of the previous year problems. But there will be some selected questions which might not belong to this category. Never be frightened, because this is the case with all the students, not only you. It will be the case with majority of the students. The only way to overcome is that taking the test series seriously. Whatever new learnings are there, whatever new things are there, ensure that you are making a report of it. And whenever you're going for the next test, you go through it and then go for the examination, next test series. Okay, so in this way you will be taking your learnings with you. Sir, any tips to score out of I think if I'm able to interpret your question correctly, Siddiqui, so you are asking that how to score full marks in signals and systems. Is that correct? So if this is your query, then it's very simple. Take your test series seriously. Whatever test series you are writing, whether it is a subject test, whether it's a chapter test, or it is a mock test, take it seriously. Try to understand where you're making mistakes. Because there will be some questions which will be given in your test series just to surprise you. Okay, it is not that they are important in the examination point of view. Just to surprise you, they will be given. Take it as a learning. Don't be demotivated because of that. Okay, just to try to attempt a particular question. If we are, generally by now, when you're solving more and more problems, your logic might have been improved a lot as compared to when you have started your preparation. As compared to that time, now your logic might have improved a lot. Just try to use that logic. Whenever you are not able to solve, come back and then see. Okay, so whether why you are not able to answer the problem. Okay, number one. Number two is that write the short notes for the signals and systems. Please write your short notes and ensure that you are revising the short notes before every examination. Ensure that you are revising your short notes before every examination. That's it. Nothing else to be done. Okay, nothing else to be taken seriously. So there is a question from Shiv Prasad, how to prepare for ISRO interview. I'm sorry, Shiv Prasad, I think you have asked this question previously also. I could not make time to answer, but now I can answer this question. See, ISRO interview is one of the very good experience for any student going for the interview. Okay, so first of all, you have to congratulate yourself that you have been selected for interview of ISRO. Okay, that itself. And second thing is that going there, attending the interview itself is a privilege for you. Okay, now coming to what are the areas you have to prepare. First thing is that you should select at least 3 subjects where you are confident in. At least 3 subjects where you are confident in. You have to, whatever subjects you are having as a part of the syllabus of ISRO, you have to shortlist a few subjects which you are interested in. And then you ensure that your basics of that particular subject are clear. Your basics of the subject are clear. If required, you can go through the textbooks also. Basics have to be very clear. And second thing is that whatever questions have come in your examination, whatever questions have come in your ISRO examination, try to solve those questions once again. try to brush up the concept of those questions. Whatever questions have come in the examination, there might be a chance that some of the questions you might not have been solved, right? So please go through the concepts of those questions, and nothing else is required. Stick to the basics, and then solve the problems of the paper that you attempted, for which you have been shortlisted. And third thing is that you go through the website of the ISRO. That's very important. You go through the website of the ISRO, see the current developments, what are all the things that are going on, try to relate with your subjects. Try to relate with your subject. This is very important, my dear student. Shiv Prasad, this is very important, that you have to try to relate whatever works that are going on in ISRO, try to relate it with the top your subjects, whatever your favorite subjects are there. Try to relate as much as possible. And that's it. Nothing else is required. Okay. So this brings us to the end of the session. I hope you had a very good time in complete signals and systems. There might be students who have missed the part 1 or part 2, or even part 3. You might have come at the end or in the middle somewhere. If that is the case, please ensure that you are making time for watching the part 1 and part 2. Why I am recommending you? First thing I have targeted as a part of this session is that all the common mistakes that the students do. All the common mistakes that the students do as a part of signals and systems, I have accumulated all of them and presented in the form of quiz questions and signal booster questions. Okay. Second thing is that if you are able to spend, so we have just taken 5 hours of your time. So just invest this 5 hours. In this 5 hours, we will be completing the revision of the subject. You will understand what are the areas which are important in the examination just by going through this 5 hours of the session. So I would request all of you to take this session seriously. If you are watching it recorded, then for every question, you pause the video, you solve the problem, and then see how I am solving the problem. Okay, whatever mistakes you have performed, try to ensure that you are overcoming those mistakes. Okay, you are documenting those mistakes. Okay, so this brings us to the end of the session. If you haven't liked the session, please like the session. If you have liked it, please click on the like button. In fact, you can also share these sessions with your friends so that they are also getting benefited because of these sessions. And if you haven't subscribed to the channel yet, please subscribe to the channel and click on the bell icon. I wish you all the very best for your GATE examination, and also best wishes for the signal booster sessions. These sessions are GATE booster sessions. I'm sorry for that. And these sessions are very important for you, and it will actually prepare you for your GATE examination. Wish you all the very best and take care.